Hello and welcome to PicoBYTE. Oh, hang on. Oh, one sec, just a minute. Hello and welcome to PicoBYTE. I'm James and we're in our new lab studio, and this is your monthly top tip to help you get out of the PicoScope friend zone. In today's episode, we're going to be understanding the I2C serial protocol and how to debug it using a PicoScope, like this 2204A. So get your scope cocked and we'll jump right in. I2C is a term that may have cropped up a few times when making a prototype where your development board may be talking to a module such as this LCD panel. So what actually is I2C? Well, we've asked our resident Pico expert, Dr. Trev, for a bit of background info.
Thanks, James. We'll make it disappear now. Inter-integrated circuit is a low-speed serial data protocol commonly used to transfer data between multiple components over a short distance. Initially developed in the early 1980s by Philips Semiconductors, it was subsequently picked up by other companies throughout the 90s. Despite its low speed, it's widely used because of the two-wire simplicity and low cost, therefore built into most microcontrollers nowadays, like this Arduino here. Thanks, I'm not finished yet. Yeah. I2C consists of two data lines, SCL, the serial clock signal, and SDA for your serial data. The voltage range is 0 to 3 or 5 volts depending on your device. For example, a Raspberry Pi operates at 3.3 volts, but an Arduino would operate at 5 volts. To control this voltage, I2C uses an open drain configuration, meaning each end has a transistor to pull the line to ground to make it a low signal. This raises the problem: if both transistors aren't active, it will leave the signal floating. To fix this, I2C needs a pull-up resistor around 4.7K to make the signal high. The resultant circuit will end up looking something like this. This results in a signal staying high when not transmitting.
So what we have here is we've got our Arduino and our LCD, and they're both powered by the Arduino. So with the I2C, we've got two 4.7Ks, which are pulling these two SDA and SCL lines high. So the green and the orange is the SDA for continuity, and the yellow is SCL. Cool. On the Arduino, we have a simple script which is just going through some quick messages, sending them to the I2C on the back and populating it onto the front of the LCD. Cool. Right. So what we're going to do is put channel A on the SDA line, like so, and then ground it. Make sure to ground your oscilloscope probe. Beautiful, still doing the same thing. Let's play. Oh, there we go, that's beautiful, absolutely beautiful. And we're gonna take our second probe, our channel B, and put it on top of our SCL line. So if we turn these channels on, we should hopefully start to see some data. And lo and behold, we are. So now we have our data on the screen. What we're gonna do is go to our PicoScope 7, go to our trigger settings, and then we're going to change the trigger to a pulse width. If you make sure to watch our trigger episode, you'll know everything about all the triggers on PicoScope 7. Now we've got it triggering properly, we'll set the mode to repeat so we don't get the auto timeout, and then we can see our data. Okay, so if we zoom into our data, we should start to see some actual peaks and troughs of our data, and you can see there we're getting all of our nice square wave and a lovely clock signal coming in. Right, from here what we'll do is we'll use our cursors, and then we'll see how long these little pulses are, because that will tell us the frequency of the I2C. Right, so what we can see here is we've got a 100 kilohertz or 100 kilobit signal. So we can use that when we run our serial decoder. So what we'll do to run our serial decoder, we'll go to our serial decoding menu, select I2C, go to next, and then select A for our data bus and B for our clock. And then it's set to 100 kilobits per second because that's what we just measured. You can change some of this data if you fancy, and then we'll go finish. Right, so this is our data. So we'll zoom out. Wow, good data. So as we can see here, we've got our first packet, which is basically setting up the LCD display for each message. So the address is displayed here as a 7-bit address, as of which it is address 27. So the Arduino will be talking to the LCD at address 27. So as you can see here, we're also getting an acknowledge from the LCD telling the Arduino that it's getting a signal. So what we're going to do is we're going to take all of our data and we're going to put it into an Excel spreadsheet and make sure we're actually getting the data we want to the LCD screen. Right, so what we can do from the PicoScope software is actually export our data to a CSV file for us to be able to look through it separately. So I'm just going to save that now as today's date. Save. Okay, so what we can see here is the data you're going to get out from your CSV file. So we can scroll along and see our data in a hexadecimal number. So from this, we can sort of work out what our I2C is doing to produce data on the LCD screen. So we can just go through all of these and take the first nibble of the byte and we can figure out what it is. So this first command we send to the LED is a 00 command, so sets the cursor to the front. And the next command is hexadecimal ASCII for space. And then we've got a P and then L and then E. And then just like we see here, it's flashing between please, hold, and testing, showing that our data is in fact correct. Right, so now I'm going to disconnect our LCD screen and you should see something different on PicoScope 7, showing that there's no acknowledgement from the LCD. So as you can see right here, we're getting a 1 from the I2C acknowledgement, meaning that there's nothing coming back from the I2C peripheral you have attached to the Arduino controller. And it's just redoing that per each byte of the information and it's not getting anything back. So if we connect that back up, then we should start to see data again. And you can see we're getting an orange on the acknowledgement, which means we're getting data through. And that's just one example of using I2C in a dev environment or a prototype, and then you can put that into an actual product and make it look awesome. So what we have here is another example of I2C. We have a smart battery system with some little commands you can send to it and see what kind of voltage it's at, what temperature it's at, and everything like that. So I've hooked up the probes. We've got SDA as our channel A and then SCL as our channel B. All plugged into a 2000 series, and then we're going to see what comes out on the other side. So on the screen, we have our command sender, little apparatus from Linear, and we have our PicoScope 7, allowing us to see the data coming through and to make sure it's actually doing the right thing. So let's jump on in. So what we have here is our device address, which is 16, which we can see, and we've got the device command, which is 09 in hexadecimal. So that command is basically asking, what voltage are you currently? If we set our scope to see a single, and then we press send, we can see our data come through. So if we verify our data byte by byte, we can see that the address doesn't look quite the same. So the problem with that is that the Linear program is using the read and write bit as part of the address, meaning it's 1 bit extra. So as you can see, as we look into each packet, the address plus the read and write bit is 16, whereas normally it'll come out as 0B. And you can see our data has been acknowledged by the smart battery with the little ACK as 0. And then you can see the data going through, which is 09, a command asking for voltage. Now, what we're getting back is pretty much exactly the same. So we're getting the same address with an acknowledgement from the controller, and then we're getting a 39 and 2F, which roughly translates to 12,089, which I assume that's in millivolts. Yeah, millivolts. So that's 12 volts. For this smart battery system, if we send an incorrect packet, then the smart battery literally just won't respond. So if we try that now, so I've got a byte of 24 going in, and we'll press play and see what happens. So as you can see here, we're getting an acknowledgement from the smart battery, but it's not sending any data back. So the controller responds with a NACK knowledge. So the data coming back is incomplete. Now you're happy with debugging I2C using a PicoScope. If you have any more questions on I2C or debugging using your PicoScope, you can leave a question in the comments or go to our A to Z in the link below. As always, make sure to subscribe and ring the notification bell to keep updated on our latest PicoBYTEs. See you next time.